Well, I hope today all the technology here works, since we are really dependent on computers today. I hope you are able to install some of the, at least some of the software on your computers I showed to you. So today we are going to talk about numerical electromagnetic simulation of antennas. So so why do we start with numerical simulation of antennas? Why do we need it? There are several problems we cannot solve analytically. With antennas, we looked at the electrodynamics course. At the antenna course, we only looked at simple analytic solutions where we knew the distribution of currents on the antenna structure, or we replace known field on an aperture with equivalent sources. Now the issue is when we do not know the distribution of sources, how to solve such an antenna problem. And there are different numerical ways we can do that. And in the first hour, I'm going to briefly discuss this will be just a conventional lecture. How do we attack such a problem? How do we handle such a problem with numerical methods? And compare also different methods, understand the difference between different tools. Because in antenna simulation, you have free tools that you can just download from the internet and use them. And you also have tools where you have to pay for just a license for just one user for just 1 year, 10,000 euro. And this is HFSS. And these guys are, the owners of HFSS, are fighting very much every piracy. So if you are going to run on your computer, if you are going to run a pirate version of this software, you may have the police knock on your door. They are able to do that. They did that to us. We did not use it, but some of our students maybe used a pirate version of this software. So you can get into troubles. So these guys really fight their things very hard. So let's try to understand what happens now with electromagnetic simulation. What are we going to do? We can start everything with just Maxwell equations. And for antenna work, it's really useful to work in the frequency domain. Antennas are usually narrowband devices. An antenna that has more than 10% bandwidth of the central frequency, it's already a very, very, very wideband antenna. We seldom use equations in the time domain, though it can be done in numerical. It can be done. Sometimes this is very efficient to do it in time domain. But trying to solve equations in the frequency domain, where we replace derivatives, special derivatives like the nabla here, the curls here, the two curls, the divergence here. We replace them with differences, finite differences between neighboring elements. If we have, usually we just have simple matter. What I mean here with simple matter? With simple matter, I mean that the permittivity and the permeability are just scalar constants. The space is isotropic, and these are not the functions of the space coordinates, except for jumps from, say, from dielectric to free space or vice versa. In electrodynamics, we have to use the differential form because we know also Maxwell equations were first written down in integral form, but integral form is very cumbersome, and further, integral form, it's very difficult to handle electrodynamics. It's very difficult to handle delays if the surfaces, the volumes, the lengths are comparable, the delays caused by this, the finite size of our components are caused by very large phase shifts. And then we cannot use the integral form. So mostly we use the differential form, and that's okay also for numerical calculations where we can replace real mathematical derivatives with finite differences between two points in space. Okay, having to calculate all these things, things are simple to calculate as long as we have Cartesian coordinates. What does mean Cartesian coordinates? In the numerical world, the Cartesian coordinates means that we have a cubic grid, a square grid in 2 dimensions, a cubic grid in 3 dimensions, where all 2 dimensions or 3 dimensions behave exactly in the space in the same way. When we have arbitrary coordinates, and arbitrary coordinates happen quite frequently in engineering. Frequently we have cylindrical geometry, or we have even spherical geometry. Also cylindrical geometry in antenna is quite common. With cylindrical geometry, of course, we have to take account of the scale factors when calculating the derivatives. It doesn't matter whether we do this analytically, we can also do this numerically, and we have to take care about that in our programs. Maybe you remember with electrodynamics, we already said that a direct solution of the Maxwell equations was not very practical theoretically. Well, it can be done practically, but still we have to consider singularities. Singularities because we have many derivatives here, and we are really working, we really get into problems with singularities here. We can, from the Maxwell equations, we can derive the equations, and the simple problem we were talking about, this is really the simple antenna problem. When we know the sources, when we know the currents, the current densities, when we know the charge densities, we calculate from them the fields. Something that is useful to do is to introduce the Laplacian operator. The Laplacian operator, why? Because this curl of curl is something really difficult to calculate. The Laplacian operator, at least in Cartesian coordinates, say in rectangular or cubic coordinates, if you are thinking about meshes, grids with standard sizes, selected sizes, the Laplacian operator is much easier to handle. It also has a simple physical meaning, but unfortunately, we were not able to do that in electrodynamics because we didn't have the time to work with numerical methods also with electrodynamics. And we got already these 2 equations, the wave equation for electric field and the wave equation for magnetic field. We already got them in electrodynamics. We already developed them, and we said that these equations, at least theoretically, they are useful when we have no sources. When the space we are calculating these equations, there are no sources. Sources must be somewhere. They must be somewhere. They must generate the field. But we do not have the sources inside the volume where we are solving these equations. There we don't have sources because we have several differential operations here. We have the nabla operator on the right side here. And that's really difficult to calculate nabla, which is a differential operator, over a source that has jumps. For instance, here we may have just in place of distributed charge, we may have point charges. And of course, we cannot calculate nabla on point charges or on currents flowing through thin wires here. Calculate the current on nabla flowing through thin wires. Even that is a problem. So we didn't find them useful in the analytic work, but maybe numerically we can do something. Because I said Laplacian may be quite simplified in numerical solutions. What we are going to do, we are going to introduce potentials. Potentials are an intermediate quantity from the sources, current densities, and charge density, charge densities, to fields. We actually want fields here, but our information is hidden in currents. In currents, in the electrical current density and in the charges, in the sources. So if we did that in electrodynamics, we get here really, if we just try to introduce potentials, this equation, this is the definition of the vector potential. Is here. If we just put in this equation together, we get a complicated equation that includes both currents and charges, and includes both vector potential and scalar potential. So then we're in trouble. But something that we didn't consider in this definition of potentials, we didn't consider that we just only defined here the curl of the vector potential. We didn't say anything about the divergence of the vector potential, and curl and divergence are two completely independent mathematical operations. Say if we have a function here, A, the vector potential A is a function of 3 coordinates, it has 9 possible derivatives, 3 coordinates, 3 components of the vector. And 3 of those derivatives are inside the divergence, and 6 of those derivatives are inside the curl. And so the curl and the divergence are two completely different independent operations. So it makes sense to introduce some expression for the divergence, and the most convenient way to do is the Lorentz gauge. The Lorentz gauge actually connects the divergence of the vector potential to the scalar potential. Doing this, the complicated equations we get from the Maxwell equations, starting here, the complicated equations turn down into two completely separated wave equations, differential equations, where we, of course, in the wave equations has the Laplacian here. The wave equation, we have no derivatives on the right side. On the side of this, we have no derivatives over the sources. And as I said, sources may have, our simplification may be that sources have quite a distribution that has singularities. We do not need any singularity, we do not need any differential operations over the sources, and that's the real value of the potentials, introducing potentials. Inside the wave equation itself, we get always a constant that's omega squared times permeability times permittivity. This constant here, we also had the same constant. We had the same constant in the wave equation for the fields, direct for the fields. This constant is also called the wave number k. So this is k squared, and here mathematicians are very happy that they have a square constant here, because they can solve this equation easily when there is a square constant available here. And this is actually our k, our wave number. Wave number, what does it tell? Wave number tells about the spatial dependence of the phase. So it's a unit, it's radians per meter. So it's by how many radians the phase changes over 1 meter of distance. So this is, it really has a physical meaning, and we call it wave number. Usually written together, wave number. Most interesting for all about this is that these two wave equations, though they still look complicated, we have the complicated Laplacian here, but they have a quite simple analytic solution, and this is what we used in our analytic analysis of antennas. But we are also going to do that in the numerical analysis. You will see immediately why in the next few minutes of this lecture. So we have analytic solutions for the scalar potential and for the vector potential. The coordinates r, without the prime sign, are the coordinates of the point where you observe both the potentials and the fields. Why r prime here? R prime are the coordinates of the sources. We may have currents, and currents must end up into charges. So if the current is flowing somewhere, charge must be accumulating there. If the current is flowing out of some volume space, then charge must be disappearing there, must be vanishing there, so we get negative charge here. So charge and currents are connected together with the continuity equation. They are not completely free. Outside this source, we have free space. So here we all have free space with no currents and no charges. There are analytical solutions that are quite useful for us. Why? They contain integrals. They contain integrals over the sources. So we sum the influence of all the charges to get the scalar potential. We sum the influence of all currents to get the vector potential. Of course, since currents have a direction, they are vectors, also the vector potential must be a vector here. The integral is very useful because these two, the distribution of charges, the distribution of currents, may have singularities, but these singularities are eaten up by the integral. So that's the real trick. Of course, we have our wave number playing a role in all these equations here. What is interesting is that with these two expressions for the scalar and the vector potential, if I know the distribution of my sources, I can calculate my potentials and furthermore my fields anywhere in space. So this we already did all this at the equations. I'm just at the course now of antennas. I'm just repeating things we did, but let's see how these things add up in a numerical calculation. In a numerical calculation, where is the problem? We have a wire. The wire has somewhere a generator in the wire that runs some current in the wire, some current I that can be calculated. From this we can calculate the current density. It's the current simply divided by the cross section of the wire. We also get charges on this wire because we have capacitance. In the near field, the wire has capacitances from the wire to the same wire, from the wire to the surrounding. So we have charges accumulating on this wire. Charges and currents we have on the wire. And from this, if we knew these currents and these charges, we could simply calculate, so we simply use the integral solutions for the potentials, and then take the curls, take the curl for the magnetic field, and take the gradient here for the electric field. And that's it. The real problem is we don't know where the currents are and when the charges are. With the prime sign, I always always want to indicate that has to deal with the sources. All quantities dealing with sources have a prime sign here. The issue is how to find these two, because we don't know them in advance. We did some guesses. If you remember, with thin wire antennas, we said if the wire is very, very thin, then we have approximately a sinusoidal current distribution. But that was just our guess. That is not necessarily true. Now, to calculate any kind of antenna, we have to find a method how to find the current distribution, how to find the charge distribution on our antenna. And that's the real difficult antenna problem. We didn't deal with this problem yet at our antenna course because we couldn't solve it. And in fact, the solution is complicated. We can, from both potentials, we can also calculate the field directly. So if I know how to calculate the vector potential, from the vector potential, through the Lorentz gauge, I simply replace also the scalar potentials here. I can calculate the electric field. So I have a relationship from the current to the electric field. Because the vector potential, we expressed it purely with the current. And we are using the Lorentz gauge to replace the scalar potential here. Now, what is our equation? We have to get an electric field from the Here, this is repeated. This dot repeats those here because it's a scalar product here. We have to be very careful what are the derivatives calculated. So this nabla is calculated over the coordinates of the field. This r means here of the field, coordinates of the field. So r are the field coordinates, r prime are the source coordinates. We get such an equation. Okay? If we know I of s prime, we can calculate E of r. Now, the real problem is reverse to this, what we have here. We know E. We know E on the wire surface. We know E on the generator. If the wire is good conductor, then the tangential component of E, that parallel to the wire, should be 0. Because wire is a metal, if it's a good conductor, the tangential component is 0. Over the generator, we also have some electric field that is proportional to the voltage of the generator divided by the dimension d of the generator. So we know the electric field all along the wire, including the generator. We know this, and we have to solve this equation in the reverse order, solving for I of s prime. And this is called an integral equation, because we have an integral inside and our unknown is hidden down here under the integral. We know the direction of the current because the current flows along the wire, at least as long as this is simple, but we don't know I of s. And that's a simple explanation what happens with antennas. We have no closed form solution for integral equations. There are no closed form solutions except for the, as I said, except for the sinusoidal approximation for very thin wires. But that's not what we would really like to do here. We would like to get a solution for any shape of wire, for a wire, maybe not just a single wire, maybe many wires, maybe a mesh or a grid made from wires, and so certainly we cannot expect to have sinusoidal distributions of currents over there. We cannot guess them. We cannot guess them. We cannot solve this thing analytically. What we can do now with numerical methods, we now split the wire into segments. And so it's the same wire as we had on the previous picture, but now it's split into discrete segments here. And our numerical approximation for the distribution of currents is now simply a column vector here. This dot here means just that this is repeated though. So from I1 to IN, all the segments of this wire. We also have a segment where there is a generator. And these segments have mutual impedances. So each segment generates a field on itself and a field also on all other segments, an electric field. And we express this integral, the solution of this integral. So in this direction, now we put in a known current and we calculate the electric field. We can calculate all these dependencies, and we call them Z here. They are not really impedances because we go from currents to fields. We do not go to voltages. We should still multiply them with the lengths of the wires. But we can calculate this matrix here. To have a system, find a system of linear equations. And with this system of linear equations, what we know? We know this column vector here. This has mostly zeros, except for the generator, if we simplify the generator with a simple segment. We may also have more complicated generators that have more segments here. All the other elements of this column vector here are equal to 0. We know the mutual impedances here, so this matrix of mutual impedances. We can calculate them, solving this equation for every single wire segment to itself and to other wire segments. You can calculate this. And now we have a system of linear equations. The unknowns are hidden in this column vector here, ranging from I1 to In. These are the unknowns we have to solve. As soon as we have calculated all these components. So the matrix here of this equation, system of equations can be calculated analytically using this equation here. There's an integral inside here. Okay, there's something difficult. This gradient and the divergence here are difficult to do. We have to calculate this thing. And this is now the idea behind numerical calculation. The idea is that we represent the current, our current with a number of segments, and I calculate the current inside each segment. This current might be constant in each segment. It is usually beneficial to use some different distribution. Maybe constant, maybe triangular, maybe sinusoidal, this current. And in fact, the software we are using is calculating these things with sinusoidal currents. The advantage of sinusoidal currents is that this ugly thing here, this is ugly, has an analytical solution. So if I have a sinusoidal current distribution, that it's exactly sine of kz or ks here, where k is the wave number, then this thing has an analytic solution, and at least calculating our matrix, it's not that difficult. It's still time consuming. Numerically on a computer, it's still time consuming, but it is straightforward. We do not need to perform numerical calculations here. We just calculate analytically each of the members here, and then we have to solve this system of equations. So this is called method of moments. Method of moments, we are putting here a criterion that we have, say, electric field equal to 0 on this segment. We cannot say all the segment. We can just choose a suitable point of this segment. So we just have one equation for every segment and one unknown for every segment. So we had one condition for every segment. That one condition is electric field is 0, for instance, in the center of the segment. And we have one unknown per segment, one current per segment. The more segments we use, the more accurate will be the solution. Don't forget that this thing may be time consuming. Why? Here we have a square matrix. This matrix, if we have n unknowns, has n squared elements. If we have to calculate n squared elements, and that's pretty time consuming. Further, the solution of a system of linear equations, it's straightforward. We can use the Gauss elimination here. That's very simple. But also this solution is quite time consuming. It grows as n to the cube, n to the third power. So this may be very time consuming. So if I have here 100 currents, I have 1 million operations to solve this system of equations for 100 currents. That's lots of work. And it's growing quickly with the third power. So it is not that simple. Life is not simple numerically. Life is not simple. What do we do in our segments? Say, our wire is made from metal. And where is the trick now to avoid singularities? Because we do have singularities here. We do have differential operation of a current that may flow through a thin wire. We are quite close to the singularity. So the trick is to put the current, to replace the real distributed current over the cross section of the wire, to replace this current with just a single current that flows in the center of the wire. And put our condition to have the tangential electric field on the surface of the wire. In this way, we have some distance, and this distance is actually the radius of the wire here. So we do not get in singularities, because if we requested that the field be 0 inside exactly in this place where the current flows, then we get to infinity, immediately to infinity. Immediately we get into the singularity with our equation here. So this r minus r prime becomes 0. That's a big trouble when you have a 0 here in the numerator of a fraction. That's infinity immediately. So you immediately get into troubles. So the trick to avoid this is to put the current in the center of the wire. And the current in the center of the wire, if we have here circular symmetry, is equivalent to the current that would flow through the whole cross section of the wire. And we only request the field to be 0 at the surface of the wire at a distance of the radius of the wire. So this system, when does it work? The way it is depicted here. It works when the wire is still thin with respect to its length. The length of the wire is d, and it should be thin with respect to the length. So our wire should be much smaller than the length of the wire. With the current software we are going to use today, with the NEC2 software, it is required this radius of the wire should be at least 8 times smaller than the length of the segments we are using. And if we accidentally define 2 short segments, the software is going to warn about that. You are outside our approximation. And also the length of the segment, if we are trying to find the current distribution along our wire, the length of the segment should be much smaller than the wavelength. Usually we need at least 10 segments per wavelength. This is for better accuracy, we may put both more segments, but as we make segments shorter, this condition may no longer be valid. So we have to be careful how we choose the length of our segments. We can also put other things inside our segment. So we said that most of our antenna is wire of good conductivity, say a metal that has almost 0 resistance. But we may have a generator somewhere. How do we install a generator here? We install a generator inside a biconical line that has some defined behavior, some defined characteristic impedance. And this biconical line adds up exactly at the ends of our segment. So this is the way to put a generator inside. We can also put some loading inside the wire. Say this wire may not be a perfect electrical conductor. May have some resistive losses, and if it has some resistive losses, we can here simulate these resistive losses with a resistor, again a resistor put inside a biconical line, so that we have the geometry pretty well defined, and this is infinitesimally small. Not just a resistor, we can put any kind of load here, also a reactive load. A reactive load may be a capacitor. We may put a capacitor here. We are not usually going to put that many capacitors inside the antenna. Sometimes we need capacitors for impedance matching, like a gamma mesh circuit. But for us it is much more important that in this way we can simulate dielectrics, because the solution of the retarded potential only works in homogeneous space. So epsilon and mu have to be constant all over the place. If we have some additional dielectric, then we can model that dielectric with additional capacitors inserted in our structure, and that's the trick. So we can extend our method of moments here also to space that contains some dielectric. And that's the important point for us. And I'm going to show you later on in the next 2 hours what are we going to do here. Next problem we do not only have antennas made for wires. Wire antennas are the simplest one, really. We have antennas made from metal surfaces. And whenever we have a metal sheet, a thin metal sheet, we can replace that thin metal sheet with a wire mesh. Usually we use a square mesh, so D is the same in both dimensions. And now the question is, what size of mesh do we need to accurately represent this thing? Okay, the side of the mesh is usually one segment long. It can be made more segments long, but one segment is enough already to have. But still, the period of this mesh should be much smaller than the wavelength. At least 10 times smaller here than the wavelength. Now the issue is if we replace a real thin metal sheet with a wire mesh. What size of wire, what radius of wire do we have here? We have to use. And that is where the equal area rule applies. If we know the area of the opening inside the mesh, this area of the opening, say AM, a mesh, should be exactly the same as the area, as the surface, not the start and the end of the wire, but the outside surface of our wire AS. So AM should be equal to AS. This brings up the most accurate simulation. And this does not only apply to electromagnetic simulation, it also applies to mechanical simulation, hydrodynamic simulation, whatever you want. The trick is the equal area rule. It does not only apply in electrodynamics. So this wire mesh segment should have exactly the same outside area here, this AS, as the opening in the mesh. Then we have the best possible simulation. And this is quite simple to implement in software. And we simply get to the relationship that the side of the mesh should be 2 pi the radius of the wire. And in that way, we can emulate a mesh, a thin metal sheet quite accurately. Next thing, we said that sometimes in my antenna I have dielectrics. Dielectrics in form of sheets, also in form of volumes of dielectrics. I'm only going to consider sheets here. So if I have a thin sheet of dielectric, when the thickness of this sheet is much smaller than lambda, I need not calculate things in the direction of delta here, of the thickness of this sheet, but because this is much smaller than lambda, I have very little influence on the electric field in this direction. But this dielectric field affects the electric sheet affects the electric field in the vertical direction here and in the horizontal direction. And that is where I place a capacitor mesh here. So I replace a real world dielectric with a mesh of capacitors. I will show you the third hour here how this is done in a practical antenna. What should be the capacitance of our dielectric, of our capacitors? If I have a square mesh, so both the dimensions are identical, okay, it's proportional to the relative permittivity of our dielectric. -1. Why -1? Because we have this one already included in our expressions for the retarded potentials. So I have to specify here only the difference from free space. So relative permittivity -1. If this is vacuum here, it's not the dielectric, then 1 minus 1 is 0. I have no capacitors to replace with. And this can work pretty well for thin sheets, and these thin sheets are frequently used in antennas like radomes. To protect our antenna from weather effects. These thin sheets, this is a very useful thing. We can use the method of moments. Further, there are other possible solutions for the method. You're still using the method of moments. It is not just possible to derive an equation for the electric field integral equation. We can define in some kind of geometries, we can define the integral equation for magnetic field. Here we have surface currents here on this metal box, and we have an integral equation for the magnetic field, knowing that the internal magnetic field, so H internal inside this box, should be equal to 0, because this is a shielded box. There could not be any field inside. And on the surface, these currents flowing on the surface of this metal box actually represent the jump of the magnetic field to the outside. And this is where we apply, so this is outside magnetic field calculated from the surface currents. Still, we apply this equation where we cannot apply it anywhere in space, because anywhere in space k is mostly equal to 0, but k is different from 0 on the surface of this object. And this is also built inside our software. That's the reason why I'm explaining it, though this is not made particularly well in our software. So I do not recommend using it, but I have rather to warn you about this thing. You had many examples on the web how to use the software. And people are using this thing in the wrong way. And they get completely wrong results, wrong simulation results. The condition to use this thing, this surface of this metal object should be a closed surface. There should be no holes in it. And the volume it's enclosing should be non-zero. So we should have some non-zero volume enclosed with a closed surface. And people are not doing that. People are using this equation to simulate thin surfaces. And if you try to simulate with this equation a thin surface, like we did here, a thin metal sheet, then you get immediately into singular equations, into undefined systems of equations. So the system here becomes undefined. So this cannot be done. Or if it is done, it's usually done in the wrong way and provides the wrong result. I have to mention this here in my lecture. I prefer not to use these things. I will show you practical examples how this thing works wrong in the final hour of this lecture. Yes, this is about the method of moments. We were discussing here method of moments and different ways to simulate many different structures with the method of moments. The method of moments, why? It's particularly suitable for antennas, because antennas are infinite problems in size, and because its computer requirements are pretty small. We will see that later on. But besides the method of moments, we also have direct solutions of the differential equations, like finite differences, finite elements. They may be in time domain, they may be in frequency domain. This is the way HFSS works. What is the conclusion here? We have our antenna made from metal. This is metal. Maybe this metal may be enclosed in some dielectric, and dielectric may also have 3 dimensions. We cut all the space here in a cubic grid, or a square grid in 2 dimensions, a cubic grid in 3 dimensions, to calculate directly our equations. Of course, since we have such a stupid way of simulating things with a cubic grid, we need many, many, many more equations, many, many more variables. What is worst? These methods, finite differences, finite elements, work perfectly into enclosed spaces. Like if we are calculating a resonator or the field inside the waveguide, this is perfect. Or the water flow inside the tube. We immediately get into problems where we have infinite problems, like an aircraft flying in turbulent air, or an antenna radiating into free space, into infinity. How is this thing solved? We have free space in this white space here. We may close this free space if you have some large metal structure with a perfect electric conductor, and this is something HFSS is using. But outside we also have radio waves propagating in free space. So at a sufficient distance, when we get into the radiative field, not in the reactive near field, but into the radiated field, maybe radiated near field or also far field, when we get a sufficient distance, we can put absorber. If we put here absorber here, and we can simulate absorber simply, we put the numbers of an absorber, we put conductivity in the Maxwell equations, non-zero conductivity, and we have enough layers of this absorber, the field may decay down to 0. So this computation mesh is sufficient that it extends a finite distance into the absorber to have the field decay to 0, and then we can calculate this thing without going to go with our systems of equations out to infinity. So using finite differences, finite elements, it's very necessary now to confine our problem to finite dimensions. We have here direct numerical solutions, so we are solving directly, numerically, the equations we have here, either in time domain or in frequency domain. Software may use both time domain and frequency domain. Frequency domain may be attractive for antennas because we have to solve the equations just for one frequency, but time domain is sometimes simpler to calculate, to implement, and also time domain can calculate after performing a Fourier transform, we can calculate the response of our antenna over the whole frequency range, and that makes sense. Just more than just one frequency. We will see how difficult is this with the method of moments. Becomes very time consuming, this thing. So finally, to compare both methods, the finite something versus the method of moments, we have this comparison here. So the method of moments, this is really vector, the potentials are hidden in the vector of moments. So every segment influences the whole available space. While in the finite differences, the equations are simple. Any segment only influences, or any element only influences neighbors. This is the reason why the memory size here, because I have mutual influences here, increases as n squared, while it only increases proportional to n. So, okay, 6 times n if we have 6 neighbors, up, down, left, right, and front and back. Only increases proportional to n, the memory size, and also the solution time. Here we had a full matrix. The system of equations was a full matrix with all non-zero elements, and the solution time increases as n to the cube. While here with finite differences, any element, the matrix of the system has mostly 0 elements. Most of elements are 0. There are only 6 non-zero elements in the matrix. And those 6 non-zero elements actually make our problem, the solution time, increase only by n squared. So it seems that the finite elements have an advantage over the methods of moments because there is less calculations to do. But on the other side, the number of unknowns is much larger. The number of unknowns, we can simulate quite a complicated antenna with just 1,000 segments in the method of moments. Well, this becomes 1 million in the finite elements. So here we have really large number of unknowns, and the method of moments can cope with infinite problems of infinite size, like antennas, because the field of an antenna extends up to infinity, while the finite differences only work over finite domains, say inside a resonator, inside a waveguide, inside a water pipe, if we are talking about hydrodynamics. So this is the comparisons on both, and what we can get free software, we can get free software with the method of moments. If I make a further comparison here of both methods, so finite something, finite differences, finite elements versus method of moments. So commercial simulation tools are usually why they are written in the way they are. We can use the same gridding algorithm to get the grid for the final element with any kind of problem, whether it be mechanics, whether it be static, like static of a building, whether it may be water flow inside the water pipe, or whether it may be waveguide, or whether it may be antenna. We always use the same grid, so we have the same tools to do these things, but these tools are very complicated to be set up. So the computation mesh setup is very complex. Manually, it's almost impossible to set up a useful grid. So you have to rely on the software. And the company that's writing HFSS, HFSS is a very small part of their business. They are mostly making their business with mechanics. And but they use the same grid, the same algorithm, and then the equations they are solving are actually simple. You can even have combined tools from other companies. They are called multiphysics. Then calculate both heat transfer and electromagnetic problem and water flow and so on. You have these combined tools. And antenna simulation is just a niche here. It's not commercially. People are not preparing to pay lots of money for antenna simulation, so they do not make much money out of here. Well, the method of moments is it's useful for infinite problems, like antenna problems, because have an infinite size. Working in frequency domain, radio antennas are usually narrowband, so it makes sense to work in frequency domain. Calculate just for one single frequency. Calculating just for one single frequency, we already know a lot about this antenna. Wire segment is simple. For many antennas, it is practically possible to hand write the geometry of our problem, hand describe it. We don't need a computer, or if you already do it, we will try to do this next hour. You will see that it's rather simple to do this. Mutual influences are complex. This delay eats most of the computation time of setting up the matrix. This complex exponent function is what eats the time. We have many variables, quite complex solution. And some simulations are difficult, like three-dimensional dielectrics. These are very variable consuming. While metal surfaces usually only have 2 dimensions, so it's much easier to work with. Wires have only 1 dimension, so that's even simpler to do it. Usually, method of moments is also included in the commercial simulation tools. You also have free tools here, open source. You also have free tools for finite differences at final elements. You have free tools also here. But these free tools, usually, they solve the equations for you. They know the equations, but they don't know how to place the mesh. And then there's what the problem. If you place the mesh, you are going to do it, but that will not be optimum, at least not as optimum as you can see in HFSS. HFSS is really masters this technique, how to place the finite elements in the best way. So this is for this hour. I was a little bit longer. Next hour, we will look at the method of moments in detail, try some software in detail here.